Hi, how are you doing? So I recently did a video on sort of like the most common patterns that you'd sort of like apply in interviews when it comes to LeetCode, DSA, name them. And I talked about arrays and hashing, two pointer, sliding window, walked you through sample questions on stack and queues, and say for how you, for instance, use them or apply the knowledge in interviews. So in this video, I'll talk about arrays and hashing as one of the most important concepts when it comes to DSA and how you handle questions and how this could sort of like be a savior when things go hard. So people joke that when it becomes hard, just like throw a hash map at it, and we'll try and understand why they normally say that. So I'll just turn off this camera. Okay, let's go. So like how your phone book works, for instance, you're finding a contact in your phone, it's instant, and then searching for a name in sort of like an unsorted list takes almost forever. So there are various reasons why this happens, and yeah, we'll get to know why we need to understand the concept of arrays and hashing. So what we'll uncover is, like I said, arrays and hashing, and then just like discover why these two fundamental concepts show up in probably say 30 to 40% of all LeetCode problems. So like the interviews I did on Microsoft, most likely I just like used a hash map somewhere when things became difficult. And trust me, once you get this, very many problems become ridiculously easy. So let's get into it. So the part one is what we are looking at here. So it's understanding arrays. I don't have notes, but I just like hope you'll get the concept. So ideally, when we talk about arrays, I'd use this example here where we have a row of lockers in it could be a gym or school. So each locker has a specific number, and then for this case, when referring to arrays, we call them indexes. And just like you can go straight into locker number 3 without opening other lockers, that is locker 0, 1, and 2, you can also access arrays elements in an array instantly. So just like the index, you go directly into that locker. So this is what we call O of 1 access time here. So this is what we call O of 1 access time. So you don't have to go through other elements. You just like have the index and boom, there you go in terms of like accessing the element that you want. So this is also called, we also refer to this as constant time. So this is also referred to as constant time. So where you have just like it could be an O of, say for example, okay, you won't get to O of 9 for instance, but any constant, as long as you're dealing with a constant, it just like results to an O of 1 in terms of like time complexity. So it doesn't matter if you have sort of like 10 elements, 10 million elements, accessing any specific element takes almost like the same amount of time. Not almost, it takes the same amount of time. So if you are accessing the 1 millionth row, okay, and you have its index, so what you're doing is you're just like passing the index, that is the one where the millionth element, and then you access it with O of 1 time complexity. That's how it works. So yeah, we could look at an example of an array. So what I'll do is I'll just create a simple class here. I'll create a simple class called arrays array demo, like this, and then just show you, sorry, I'm not using Java 25. Yeah, I should be using Java 25. Yeah. So how do we create an array? Very simple, int, and then you say, for example, is an array of numbers equals to, you use the static way, so 10 20 30, like that, for example 20 20, something like a 30. That's how you create an array. And then if you want to access, so we want to access element, we want to access 20, for example, let's say we want to access 30. So what we need to access 30 is just like the index. If you know the index, that's going to take you an O of 1 time complexity. So you say something like enums, like that, and then that is that, and the arrays are 0 indexed. So that means that the very first element is at the 0th index, 1, 2, and 3. So like this. So once we run this up, once we run it, we're gonna get something like a 30. So that is in terms of accessing an element using the index. So once we create an array with 4 numbers like we've done, when we write accessing nums at 3, what we are doing, it jumps directly into index 2 and gives us the number 30. So it's not gonna check like it's not going to compare, is 10 what we want? No. Is 20 what we want? No. No, it's not going to do that. So it knows exactly where it's going. So yeah, and the other thing you sort of like need to notice if you're not a Java developer, or just like I think it applies to any other language, arrays are zero indexed. So it starts from that index 0. Okay. So the other sort of like common patterns are, say for example, you want to, this is accessing by index. So this is accessing by index, which gives us O of 1. So this one gives us an O of 1 accessing. The other operation that you would sort of like look at is searching for a value. So here now we want to search for a value, and you understand, if you're searching for a value, let me just make these things unique. I'll not make them sorted. 10, 20, let me just say something like 25. So when you're searching for a value, what we are doing is we just like want to loop through the whole thing, comparing. Say for instance, we are looking for an element like 25. So what we do is we are looking for 25, right? So as we search for the value, you have to compare, is 10 what we want? No. Is 20 what we want? No. Is this what we want? Yes. So this means that for the very worst case, when the element is at the very last index, index n, so when it's at index n, this is what we sort of like look at when we want to build the time complexity, is what at the very worst case, how much or how many iterations would it take for us to get to that element. So it will take us sort of like n passes to get to that. So ideally this means that when you're searching for a value, the time complexity would result to an O of n, because you have to loop through the whole array comparing the elements one by one. And for the very worst case, if it's at the very end of the array, it means we have to go n times, or n minus 1 because of indexing here. But yeah, that's ideally what we mean. So what we mean by this is we create a loop. We could start, okay, we could create the enhanced for loop, but let me just show you using the normal one, like that, I less than nums.length, like this. And then what we want to do is we want to compare every element. If the nums that are this specific index that we want, is it equal to 25? If it's equal, if it's equal, we return the index. If it's not equal, we could say something like not found, incrementing, or just like say moving to the next. You get, so yeah, so we could run it and then you see. So if it's like I said, we are looking at the very worst case for this scenario. So we're looking for what are we looking for? 25. So let's see, not found, moving to the next, not found, moving to the next, found, not found, moving to the next, not found, moving to the next. I don't know why it's doing all these things. It should be -1, I don't know. Yeah. So I guess what's doing, like, just like looping through the whole array. So if you find it, you could do something like a break, for instance, yeah, so that we stop the execution. Yeah, we found it. Yeah, that's ideally how the lookup would work. So inserting elements at the end, this takes an O of 1, because ideally what you're doing is just like to that O of 1 if the space is available. I'm sorry for that. So if you're inserting at the end, So if you're inserting at the end, we take an O of 1, but I'll just like show you a diagram that shows all this. No. It's O of 1 if there is space. There is space, yeah. And if there is no space, it means we'd have to resize the whole array. So resizing the whole array, we now take an O of n. Because we are resizing the array, it would take. So most of the times, we just like, okay, we just have to assume there would not be there'll not like be space for you to do the thing. So if you're resizing, if there is, so this is if there is space, and then O of n if there is no space. So this means we have to resize, yeah, like that, yeah. So inside, sort of like also inserting at the middle, what we are doing, if you want to insert at the middle, is we have to shift n elements. So we must shift all like subsequent elements. So that's the whole thing. And then also like deleting from the middle takes an O of n, because you must shift elements to fill the gap. So yeah. That's about the whole thing. But also arrays could get a bit tricky while accessing is sort of like super fast. Other options could be slow. Yeah, so that's ideally it, and by that I mean like you don't know, you want to access something like let me just go back to IntelliJ. Yeah, so the thing that would make sort of like arrays slow is when you're looking for like a specific value. Say for example, you're looking for this camera, yeah, you have to check, is this a camera? No. Is this a camera? No. Is this a camera? No, till you get to it. That's what making it like a bit tricky when you're looking for a specific value. Okay, so that's ideally it. So when you're searching for a value, this is what we call like a linear search, because you have to fundamentally go through every other element in the array. That's what brings about when you're looking for a specific value, it ends up being an O of n. Yeah, like that. Yeah, so that's that about arrays. And yeah, so we can just like move on to the next thing, this other beautiful data structure, where we talk about the hash map. So a hash map, what we are referring to in this case is when we are talking about hashed data structures. So when talking about hashed data structures, we have what we call a hash function, so which is sort of like a mathematical function that ideally converts input data, that is what we refer to as keys. So there's the concept of keys. So the input, it's converting the input data, so this is what we refer to as the input data of any size into a fixed output, which is like a hash code. So for every data that you store, there's a hash code generated for that. So if you store a name like Ian, for example, so Ian would have its own hash code. So there's a hash code that is calculated for this, and every other element that you store inside these data structures, called the map, it is hashed. Everything has a hash. So there are sort of like properties that you go and look at. So good hash functions could have various properties. One is deterministic. So by deterministic we mean that the same input always produces the same output. So yeah, that's very important, and this would sort of like just ensure that things are working fine, yeah. So that you don't put Ian the very first time, it generates a hash code, say for example, or X something, and then the next time you come and put Ian, it generates like another hash code. So ideally the result should be deterministic, same input, same output. The other thing is uniform distribution. So here we're talking about it spreads the value across the available space. And then lastly, fast to compute. So when you're talking about hash data structures, when you're looking for a specific value or whatever, it's best known for this. So there's O of 1 lookup time. And by this we mean that whenever you're looking for a specific value, it's easy to find it using just like an O of 1. Okay, so this is just like a simple diagram to show you how the processing is happening, how it's being cooked. Of course, Sora did a very good job in this. So your input is Alice, you get the hash function, so it generates a hash for it, and then when you're looking for it, and it just like gives you what you want instantly. So HashMaps use the hash function to sort of like determine where to store each key and value. So like I said, a hash map is a key and value data structure. So let me just move this one a bit here. So when you're storing elements in a hash map, so this could be your hash map. So what we're having here is a key and a value. Say for example, you're storing name and say what the registration number. Okay, so the name is the key, so Ian is the key, and then the value is the registration number, or just like how your phone book could work, for example. So you have the name, and then inside here you have your phone number. So you could have the phone number here. So Ian's number is 07, whatever. So anytime you search the name, it gives you the phone number. You search for somebody like Paris, and then it gives you the phone number, if the phone number is stored there. So and the other thing is the elements in a hash map, they are unique. No, the keys are unique, but the values could be duplicate. So you can't have two Ians in your phone book. There will be a collision for this case. So there's a concept of hash collision. So because we said anytime you store Ian, it needs to be deterministic. So the same input gives you the same hash code. So you try store Ian again, there already exists that hash code inside there. So that would be a problem. So for just like this example, so the hash function is just like a magic translator. What we have here, you just like feed it with any value. For our case, we are feeding it with Alice, and then what it's doing is, in this case, Alice, and it spits out a number. Let's say it gives us like the index, or the hash is 3. So now here's the magic. So if you give it a name like Alice tomorrow, next week, or just like any other time of the year, it would always give you the 3. So the same input, same output every single time. Remember, deterministic, yeah. And when it gives you Bob, it might it might give you a 7. Charlie might be 1. The hash function distributes these names across different positions. So that's very important for you to understand. Internally, just like a hash map is backed by an array. I hope it's safe to say that. So the hash function converts the key into an array index, and then this allows for O of 1 average case lookup, insertion and deletion. Yeah. So I bet that's almost it about hash maps. So I can just like show you a very simple way of messing around with hash maps. So okay, this is an array demo, but I have a hash maps demo here. And how it works is how you create a hash map. It's pretty simple. Is you create a map. This is an interface. Okay, for this case, we're storing an int, a string, and an integer. A string as the key, and integer as the value, and then you have the new hash map here. Now, what we could do is, say for example, you want to store Ian and the phone number. So you use map.put, and then the .put takes in a key, which is for our case is a string, and then the number which we've had coded here is 792. That's how it's done. So key value when you're putting, and then when you want to retrieve a specific value, say for example you are searching in your phone book and then you type Ian. So what ideally the result that you should get, of course, it's supposed to come up with the name and the phone number. But for this case, for a hash map, of course you can get like the whole entry. That is like an entry refers to key and value, so that combination. If you want to get the specific result or phone number for Ian, you just pass in the key. So you just do a map.get, and then the map.get takes in a key. So yeah, you just like have to pass in a key, and then it returns the value. So when you pass something like an Ian, it results to a 792. The other important method that you possibly need to understand in HashMaps is get or default. So what happens when I pass something and I don't, okay, it's not there in my map. So you do something like you pass you pass Mongare, it's not in our map, you give it a default value. So if it's not there, return a 0. Ideally, that's how it works. The other important method is contains key. So you want to confirm if a certain thing exists in your map. So we want, okay, the contains key is you want to see if this specific key exists inside our map. So you pass the key, could be a string, could be an int, could be any other data type that you want. And contains key, pass the key, and then it returns true or false depending on whether or not the condition has been met. We have also like contains value. So here we want to check if this value is available inside our map. So it returns true if the map if this map maps one or more keys to the specified value. So more formally, returns true if and only if this map contains at least one mapping to a value v, such that objects.equals value is that. So this operation will probably require linear in the map size for most implementations of the map. So when you're looking for a specific value, this is gonna be a bit tricky because you might have multiple values, so you might end up with a linear time. But when you're looking for a key, when you just like pass specifically a key, because it's one, we have unique keys, so that specific key is gonna get to the to it with O of one space time. The other just like important methods that you could understand: getting the size of the map, checking if the map is empty. Here we just like going through the key set. So you want to print out all the keys. So you iterate through the key set. So you just do like a map.keyset, and then this would bring to you all the keys, and then here just like going through each and every one of them. The other one is you could do map.values. You want to go to all the specific values, and then we have this other one that is quite important, which is map.entry. So ideally, like I said, an entry is the key value, so that's a specific entry. So for every entry in our entry set, so you do a map.entry set to get the whole entry. You could get entry.getKey, and then you could also get the value and output them. Put if absent. So here we have a map and we want to add a value, and we're not sure whether or not it exists. So put if absent. So is an in our hash map. If it's not, put the value there. Yeah, and ideally that's how HashMap work. Yeah, so we could try and go through a solution together. So this is the video is becoming a bit longer, which is still okay, but the key thing is for you to get these concepts clearly and understand how you could use them. Yeah. So the other concepts that I'd urge you to look at is collision. So when collisions occur when two different keys hash to the same index. So you have a name like, say for example, okay, this is just like an out of the box example. Ian gives a certain hash, and then you have, say for example, then ideally really like this is not supposed to happen in the real case, but yeah, this is just an example. You give Dan, it gives the same hash. That is what we call a collision. So two different keys hash to the same index, which is bad. So common resolution strategies would be one, you do chaining. So you store multiple items at the same index using a linked list. So there's the concept of linked list. You also have to look at how these buckets or whatever are produced. The other one is open addressing. So what happens here is you find the next available slot to store your hash index. So and Java's hash map sort of like applies the chaining to ensure that we have good hash functions and minimize collisions, keeping operations like close to O of 1 in terms of all this. Yeah, so I hope that you now understand how a hash map works. Sorry, and yeah. So if you've been wondering how these things work, you now understand. Yeah. So the other last data structure I'll talk about before doing a simple question is the set. So the set, like your high school set, geometrical set. So you have your set, and the most interesting thing about your set is that it had one specific compass, okay, that could do a certain thing. It had a ruler, it had an eraser, it had a sharpener, it had, yeah, it just like had unique elements. That's what I'm trying to say. At no point did you have two sharpeners in your set, the mathematical set or geometrical set. At no point did you have two erasers. At no point did you have, okay, there were rulers, but they were different kinds of rulers. So we had this triangular one, you had this one that looked like this, the 90-degree one. Everything inside your mathematical set was unique. There was no duplicate elements inside your mathematical set. And this is what this translates to what a hash set is all about. And yeah, it's basically a hash map that only stores keys and no values. So that's one. So what we are doing here is we are storing only keys. We don't have like values or something of the sort. So like that. And then so we use this hash set to when we only care about does it exist. So the only thing we care about is does it exist. So does whatever we are looking for exist inside our hash map. And remember, our hash set, remember the hash set only contains unique values here, okay? And yeah, and you don't need to associate it with a specific value, and this ends up with an O of 1 O of 1 complexity for add, contains, and remove. Yeah, that's pretty much it about like the hash set. So what we are doing is we're storing unique values, and just like keys, for sorry, it's a hash map, but you're only caring about keys, and the only operation that really matters to us is looking at this hash map. Does this exist? So if it doesn't exist, you either return this. So all right, just like a quick example of hash set, and then we'll be good to go. So I just need to create let me just create it here. So shift command plus. Is it really? No. What's the command for zooming? Control alt shift plus. Okay, control alt shift plus. Yeah. So let me create a hash map with you here. So I'll not create another, or let me just create another class. Yeah, hash set demo, like that. We don't need this one. Just like come to the main, and here we just like create, we could just do a map, and then yeah, do we do a map really? Let's see. No, we do a hash set, hash set like this. It's supposed to take in what is it storing? Let's store like integer, and then we call it a set like that, and then equals to new hash set like that. So how do we add? We just like do a set dot add. Is it really? Yeah, we add a number, checking if it contains. So if you want to check if it contains, okay, let's set dot add 2, set dot add 3, set dot add 4. So check if present. So remember, we are storing unique elements. So if I do something like a set dot add 4, this ideally shouldn't work. Even IntelliJ is telling me that this is duplicate. So add specified element to the set if not already present. Yeah, so this would just like we are wasting our time, but ideally it wouldn't work. So check if present. So we have to check. We just do a boolean. So is okay, is present, like this, equals to set dot contains, you pass a 2, and then you could output it. Yeah, that's ideally how you do it. We could also try, we say set dot add, we add a 4 like this, and then what we could do first is, before adding, we could just like print out the whole thing as out. We print our set before, and then we print our set sorry, afterwards. So like this. So control function F10. Let's run it. Let's have it. Let's run and then see. Yeah. So you see what's happening. So we said set.add. So initially it had 1, 2, 3, and 4, and then now we add another 4. It doesn't add into our set. That's how it happens. So enough of the theory. At least now you understand these data structures, you understand arrays, you understand hash maps, and now hash sets. Now let's get into the thing where we talk about a specific problem, the very easy to sum problem. So we are given, so I'll just go back here. Okay. Yeah, I'll do 2 questions. So we are given a target number, and then we want to check, of course this is supposed to point here, there's an error with this. You're given an array of integers and a target sum. Find 2 numbers that add up to the target and return their indices. So just like a walkthrough is, you're given a target and then you're given an array. We want to find 2 numbers that add up to this target and then return their indexes. So ideally, how you do it the bad way, or no, okay, the brute force way, is you stand at 2, compare, is 2 plus this what we want. So if this was not like what we wanted, our target sum wasn't like 9, we'd do, is 2 plus 7 what we want? No. Is 2 plus 11 what we want? No. Is 2 plus 15 what we want? No. Come here now. So we don't need this because we're already done. So 7 plus 11 what we want? No. 7 plus 15 what we want? No. Come here now. 11 plus 15 what we want? Yes. Return the indexes. So that's ideally how you sort of like think about it, without like considering other data structures. But now, so yeah, that's ideally the brute force. And for this, because you're sort of like having 2 loops, you'd end up with a time complexity of O of n squared, and because you're not introducing any other data structure to store the elements, you end up with an O of 1 in time complexity. That's the brute force. So now, what is the thing that we're getting from our approach? So the key insight here is, for every number, we only need to know if it complements, like, or if its complement exists. And complement is just like 2 plus 2 equals to 4. No, 2 plus 3 equals to 5. So 2 is a complement of 3 when it comes to like attaining a 5. That's a complement. So we want to just like find if it exists, does it exist, and if it exists, where does it exist, like that. So so problem 1, to sum, this is just like a LeetCode problem that is easy to understand, and I've shown you how the brute force approach would be. So if I'm to show you, let me just create it here, or in arrays demo, the brute force approach would be simple. We do something like this, so no need to create a method. So we just say for, and then we start from the first index, int I equals to 0 like this. We get up to nums.length, and then we create another for loop inside, and then this for loop needs to start from I plus 1. So yeah, so this is the external for loop, and then the internal for loops need to start from here. So when we shift this index to 7, this internal for loop needs to start from here. So ideally the concept is, when we are I equals to 0, j starts from 1. When I equals to 1, j equals to starts from 2. So here the concept is I plus 1, j equals to I plus 1. Yeah, so that's just it. So for int, say something like a j equals to I plus 1 like that. We iterate up to the last element. So what we need to do is just like check, do the check here. So if nums at I plus nums at j, if it's equal to say for example our target, target like this, what we need to do is we need to return the indices. So return the I, so it's a new int array, and then it contains our I and j like that. So let me just create a simple target here. So say int target equals to something like a 15. So ideally that's how our method would sort of like look like. So of course it doesn't work here because I'm creating inside a method, so I can't return because this it's a void main. Yeah, I didn't want to go the hassle of creating a new method, but ideally this is what we refer to. Yeah, so yeah, that's ideally how the brute force approach would look like. Now I could just repaste it here. So if you're to create your own method, you could say public static int like this to some like that. It's taking an int arr or say nums like that, and then it has a target like this, like that. Now this would work. If it misses, we return say something like a null. We could return a null or whatever, or an empty array. So that's how the brute force works. So for the worst case here, you'd end up with an O of n squared in time complexity. This means for 1,000 elements, we'd need 1 million checks. That's very slow. Yeah, and that's some seconds you're wasting. But now with a hash map, we can do this one pass, just like reduce O of n squared to O of n time. So how do we use a hash map for that problem? Is the key insight we're getting here is for each number we ask, have I seen the complement before? So if you've seen it, if I'm at, say for example, I am at this, so if I'm at 7, okay, we do 9 minus 7, we get 2. So if you had stored these 2 somewhere, you just get it from that map, and that would take you sort of like an O of 1. Getting that would take you an O of 1. But because we are in a loop, I'll show you, we just like end up with an O of n. But ideally that's the concept. Have I seen 2? If yes, we're just done. And it's that simple. So how we do this is I'd take this. So let me see how long we are currently at. That's 38 minutes. Oh, crazy stuff, you know. Okay, so if you are, let me take that one here. We'll do it here like this. Now we want to do away with this inner loop. So here we are doing the famous computer science trade-off. We are trading space for memory. So what we do is we just create a hash map. Okay, you could use the interface, which is okay. A hash map, we create a hash map, and then now this is the hash map is storing what we are storing in the hash map is the key value, which for our case is the specific number and the index, yeah, like that. So we look at this here. So what we are doing is we are now introducing the concept of getting a complement, and this complement is simple. It's just like target minus the current number that we are at. So yeah, we have 2, 7, 11, 15. So we are currently at 2. We get the complement, which would be a 7. So what we need to do is we need to check if the complement, so we do a map dot contains that complement. If the complement is in our map, we just like return sorry, I'm using autocomplete, just want to save on time. But we return a new int that gets, we do a map dot get complement, is it returns the index of where our complement is. So if we were, this is our array 2, 7, 11, 15 like this. So if you are at 7, No, during the first pass, we'd get a 7. So is 7 in our map? No, it's not there. We move on to the next element. So we just like put the current, we put the current number, which is 2 in our map, and its index. So at first, our map would contain 2 and index 0. Next, we add 7. So we do a complement. Complement is target, which is 9. Minus 7, we get 2. So is 2 in our hash map? Yes. Do a map.get complement. So complement here is 2. When you do a .get, you pass a key, it returns the value. So it returns 0 and our current index, which is 1. Ideally, that's how it works, and you end up with of. So here, let me just screenshot this. Let me screenshot this. Okay, we're almost done, guys. We're almost done. So paste it here. So what we are doing here is this loop, the outside loop would go n times, but the operations here are O of 1, O of 1, O of 1. Yeah, so this means that our thing would end up with an O of n space complexity. But now, for the very worst case, we'd store all the elements inside this hash map. This means that our time complexity would also be, our space complexity would also be O of n. Yeah, that's that for that. Now, our last question, we do the last question. That is the contains duplicate question. So ideally, we're given an integer array, return true if any value appears at least twice. So approaches would be 1, you sort the neighbors and check. You sort and then check the neighbors. So this would, like, the internal sorting algorithm takes like O of n log n time, and space is O of 1. So sorting is the issue. It increases the time complexity. Hash set, here we are trading space and time, so we will end up with an O of 1 in time complexity and O of n in space complexity. How it looks like, so I just want to show you here. Hash map, this is how it would look like. So you are looping through the elements of that specific array, okay? So you're looping from, say, 0 to n minus 1, the length. If you had elements like 1, 2, 3, let me use a different pen. If you had elements like 1, 2, 3, and 1, okay? So is 1 in our set? No. Add that element. So this is now our set. This is how it looks like. Is 1 in our set? No. Add it. So we have 1. Is 2 in our set? No. Add it. Is 3 in our set? No. Add it. Is 1 in our set? Yes. We found the duplicate, so don't add anything. This is how it looks like. Is 1? No. No. Add it. 2? Add it. 3? Add it. It exists. We return true. That's how the whole idea would work. So just create that method. Say public static boolean contains duplicate. You pass the array. So what we need to do here is we need to create a hash set that stores the number, and then we loop through the numbers. So here we don't need the indexes. So for int num in nums, what are we doing? We are checking. So if our set, so if we just like set, if the set does not contain, so we start by the false condition. If the set does not contain, so we are negating the thing. If it doesn't contain that number, what we need to do is we need to do a set dot add that number. No, we could do this, or okay, let's see. We check, does our set contain the num? If it contains the number, we return true. Okay. Otherwise, we add it. So if the set contains the number, return true. Otherwise, add it. If it exits successfully, we return a false if it doesn't contain the duplicate. The other way of negating is if our set does not contain the number, what we do is okay, let's not talk about this because I'll start confusing myself. But nonetheless, we check if the set does not contain the number, you add it. If it contains the number, you return true. So we just like reverse the whole thing. So this means we're just like trading. This one would come down here and then this one would go up there. Okay, that's ideally almost everything we need to understand when it comes to arrays and hashing. So there's like the concept of anagrams. Here we'll possibly do another video to talk about this so that we don't make this a whole long video, but there's that concept as well that we sort of like need to look into at a later time. Okay, so I guess that's that for now. So you just have to remember these things here. So when you're putting in a hash map, you're passing in the key and value, it stores the pair. The lookup, the time complexity for that is O of 1. Getting or retrieving, just like you're getting a value, passing in a key, that's an O of 1. Contains key, that's an O of 1. Remove, that's an O of 1. Get or default, that is self retrieval. If you don't get what is the default value, that's an O of 1. So arrays give us O of 1 accessed by index, but O of n when you're searching by value. So HashMap, on the other hand, they give us an O of 1 for everything. So insert, lookup, delete, and how they are achieving this is by using hash functions to turn values into specific memory addresses. So we've solved two problems: contains duplicate and twosome, using a hash map to find the complements, and then for contains duplicate, we're using hash set to sort of like retrieve what we've seen. So the other problems that we possibly do in the next video are valid anagram, get to see how we use this, but ideally what you're doing is just like counting frequencies and also grouping anagrams using sorted string as keys. So yeah, thank you for listening up to this very point, and do have a lovely day. If you found this helpful, remember to smash the like button and subscribe for more DSA tutorials. So drop a comment and let me know which problem works, which problem sort of gives you more trouble, and what you want me to explain next. Thanks for watching, and I'll see you in the next video. Bye bye.